Ever wondered why solar energy is a buzzword in today's world, and what factors influence its efficiency? Solar energy, the clean, renewable power harnessed from the sun, is a key player in our transition to a sustainable future. But the amount of solar radiation a panel can capture isn't just about sunshine, it's a complex dance involving the panel's orientation, the latitude of its location, and the position of the sun. Intriguing, right? Let's dive deeper into how these factors affect the amount of solar radiation a solar panel receives. Our goal? To calculate the amount of solar radiation incident on both a horizontal surface and a tilted surface of a solar panel. Now this might sound complex, but let's break it down. We're essentially trying to understand how much sunlight a solar panel can absorb. Several factors come into play here. First, we have the solar panel's tilt and azimuth angles. These essentially tell us the direction the panel is facing. Then there's the latitude of the location. This is important because it impacts how directly the sun's rays hit the panel. Next, we consider the solar declination angle, which is the sun's position in the sky at noon. We also take into account the hour angle, which changes with the time of day. Finally, there's the atmospheric path length, which describes how much atmosphere the sunlight has to travel through before it reaches the panel. Now that we understand the problem better, we can start with our calculations. With the data and formula at hand, it's time to crunch some numbers. Let's delve into the calculations that will help us understand how much solar radiation hits a solar panel depending on its orientation and the sun's position, among other factors. First, we'll need to understand the solar constant, which is the amount of solar energy that reaches the outer atmosphere of Earth per unit area, per unit time. This constant is approximately 1,361 watts per square meter. Now let's consider a solar panel tilted at 30 degrees. The tilt angle is the angle between the panel surface and the horizontal plane. In our case, the azimuth angle, which is the panel's compass direction, is 180 degrees. This means our panel is facing south, a common orientation to maximize sun exposure in the northern hemisphere. Next, we factor in the geographical location. The latitude of our location is 40 degrees. Latitude plays a crucial role as it determines the sun's path across the sky and thus, the amount of sunlight that hits the panel. The solar declination angle, which is the angle between the equatorial plane and the line connecting the center of the sun and the center of the Earth, is 23.45 degrees. We also have to account for the hour angle, which is 30 degrees in our case. The hour angle is a measure of time, expressed in degrees, that represents the sun's position in the sky. Lastly, we consider the atmospheric path length, which is 1.02. This represents the length of the path that sunlight takes through the Earth's atmosphere. Putting all these factors together, we can calculate the amount of solar radiation that strikes our tilted solar panel, and the result? Approximately 2,428 watts per square meter. This is considerably more than what a horizontal surface would receive. So, we see a solar panel tilted at 30 degrees with the given parameters receives approximately 2,428 watts per square meter, significantly more than a horizontal surface. Impressive numbers, right? But what does this all mean? Well, let's break it down. The calculations we've gone through today reveal the substantial influence that a solar panel's orientation and the sun's position have on the amount of solar radiation the panel absorbs. When we positioned a solar panel at a tilt angle of 30 degrees with all other parameters given, the panel received approximately 2,427.916 watts per square meter. This is a significant increase compared to the radiation incident on a horizontal surface. Why is this important? Well, understanding these calculations and factors is crucial if we want to optimize our solar panel installations for maximum efficiency and energy absorption. It's not just about placing a panel under the sun and hoping for the best. It's about carefully considering the geographical location, the panel's orientation, and even the celestial position of the sun. This knowledge allows us to harness solar energy more effectively and efficiently, reducing our reliance on non-renewable energy sources and contributing to a more sustainable future. So there you have it. Solar energy isn't just about panels and sunlight, it's about the intricate maths behind it all, the understanding of which can make a world of difference. This example underscores the importance of considering geographical and celestial factors in optimizing solar panel installations for maximum efficiency and energy absorption. So, next time you think about solar energy, remember it's not just about panels and sunlight, it's about the maths behind it all.